Hi everyone. Last time we've spent the whole class hour to solve end of chapter 3 problems. And starting from today, for the next couple of hours, we're going to talk about chapter 4. Okay? Okay, so this is the chapter 4 outline. So from chapter 4, we are going to learn how to solve problems using uniform series, compound interest formula, and also learn about how to apply arithmetic and geometric gradients in modeling, economic analysis. And we will also talk about how to handle if compounding periods is different from payment periods. This is somehow overlapped with the chapter 3. Also, we are going to talk about the nominal interest rate and the effective interest rate again within this chapter 4. Okay? Okay. Okay, so the chapter 3 introduced basics of engineering economy factors, such as single payment compound amount factor, single payment present worth factors. And these factors are tabulated, and they are used much more frequently than the formulas they present. And in chapter 4, we will learn about several other engineering economy factors. And the engineering economy factors are based on these assumptions. First, the interest is compounded once per each period. A lot of our example problems assume that each period is a year. However, this assumption is not needed. A period can be a year, a month, a quarter, a semester, a week, and so on, right? And more importantly, both the interest rate and the number of periods must use the same period length. Last time, several exercise problems, such as 3-29, 3-31, 3-33, deals with this issue. And later in chapter 4, we will discuss more about this issue with nominal interest rate and effective interest rate. Okay? And the cash flow occurs at the end of a period, except the first cost and the prepaid expenses. Okay? And the first cost occurs at time t equals 0. That is the beginning of period 1. Okay? And all the periods are the same length. So just to remind you, our engineering economy analysis are based on the engineering economy factors, which is based on all these 4 different assumptions. Okay, so a uniform series is identical to n single payments like this, okay? N different single payments where each single payment is the same, okay? Same height, right? And there is one payment at the end of each period. Usually automobile loans, house mortgage payments, and insurance premium, and many other loans are based on a uniform series. And these are the uniform series compound amount formula and uniform series sinking fund formula. The term inside the brackets, either this or this, are called a uniform series compound amount factor, and this inside the brackets are called the uniform series sinking fund factors. Again, I'm not going to go through how to derive these formulas in class. Instead, I want you to read our text. In pages number 104 through 106. Okay? And the formula 4-4 can be used to convert from a uniform series A to a future sum of money, which is F. Okay? Likewise, using the formula 4-5, the future single payment F can be converted to a uniform series, which is A. Okay? Okay, then let's take a textbook example, which is 4-1. You deposit $500 in a credit union at the end of each year for 5 years. The credit union pays 5% interest compounded annually. And immediately after the fifth deposit, how much can you withdraw from your account? So you deposit $500 in a credit union at the end of each year for 5 years, right? And they pay 5% interest compounded annually, right? And the question is, immediately after the fifth deposit, how much can you withdraw from your account? So from the program description, so first we are working on example 4-1. From the problem description, we know that the value of A is 500, right? And I, the interest rate is 5% over 5 years, right? So N should be 5. And we want to know the future sum, which is F. Okay? So we can answer the question by using the uniform series compound amount formula. But before we do that, why don't we draw the cash flow diagram first to visualize the current situation. So starting from time period 0, 1, 2, 3, 4, and 5. Okay? And at the end of each year, you need to deposit $500, right? So those are the uniform series, right? Definitely, those are $500. And we want to know how much can you withdraw immediately after the fifth deposit. Okay? And the given interest rate is 5%. Okay? So if you use the formula, it's going to be F equals A times I 1 plus I to the power n minus 1 over I. Another expression would be A times F given A I over n. So we are going to use this formula, right? It's going to be 500, 1 plus 0.05 to the power 5 minus 1, 0.05, which is same as 500 f given a, 5% over 5. Okay. So let's find out this factor value. You are looking for 5%. So you need to look at our text, page 608, and f given a and over 5 period, which is 5.526, right? So this is going to be 5.526 times 500. So this is going to be $2,763 even. Okay. So after the fifth deposit, you will have $2,000 Okay. Okay, then let's take the next example, 4-2. So Jim wants to buy some electronic equipment for $1,000. Jim has decided to save a uniform amount at the end of each month so that he will have the required $1,000 at the end of 1 year. The local credit union pays 6% interest, compounded monthly, not yearly. So in that case, how much does Jim have to deposit every month? So he wants to have $1,000 right after the 12th deposit. So this is example 4-2 from our text. And let's draw the cash flow diagram first. These are 0, 1, 2, 3, 4, 5, 6, 7, and so on to 11 and 12, let's say. So here there's a uniform amount at the end of each month. So after 1 year, which means after 12th month, right? He will require how much? He will have to require $1,000 at the end of the 1 year. Okay, so here F, the future sum would be $1,000. Okay, and we want to know the A value, right? Okay. Then what value you're going to use for I, the interest rate? The interest rate is based on each month, right? And that's going to be 6% divided by 12, which is 0.5% every month. Because it does say 6% interest compounded monthly. So this means that the bank pays 0.5%, which is 6% divided by 12 months every month, okay? The bank will pay 0.5% every month. And since there are 12 months in a year, the N becomes 12 months, okay? So by using the uniform series sinking fund formula, which is A equals F times A given F, I% over N period. Another expression is F times I over 1 plus I to the power I, 1 plus I to the power N minus 1. F, the future sum is 1,000. A given F, 0.5%, N is 12, right? Or 1,000 times 0.5% is 0.005, right? Over 1.005 to the power N, which is 12 minus 1. Okay. And let's find this vector value. It's 0.5% and A given F over 12 period, 12 months, which is 0.0811. This is 0.0811. So how much is that? $81.10. Okay. Okay, and these are the uniform series capital recovery formula and uniform series present worth formula. And the terms inside the brackets are called the uniform series capital recovery factor and uniform series present worth factor. Okay. And this formula 4-6 can be used to convert from a present sum P to an equivalent uniform series A. And the uniform series A can be converted to the present sum, which is P, by using the formula 4-7 as well. Okay, then let's take example 4-3 from our text. An energy efficient machine costs $5,000 and has a life of 5 years. If the interest rate is 8%, how much must be saved every year to recover the cost of the capital invested in it? So we are working on example for dash 3. So a machine costs $5,000 and has a life of 5 years, and the interest rate is 8%. Then how much must be saved every year to recover the investment? So the initial investment is $5,000, right? So if you draw the cash flow diagram, initial investment is $5,000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And for the next 5 years, we want to know that with 8% interest rate, the annual payment, which will cover this initial investment of $5,000. So we want to know the uniform series over the next 5 years, 5 periods, right? So using the uniform series present worth formula, we can answer this question, right? So we are going to use the formula A equals P times I times I plus, 1 plus I over, to the power n over 1 plus I to the power n minus 1. Another expression is P times A given P, I% over n periods. Okay. So 5,000 times I is 8%, which is 0.08, times 1 plus 0.08 to the power n is 5 years. 1 plus 0.08 to the power n, which is 5. Sorry, this is 5, right? Minus 1. Or 5,000 times A given P, 8% over 5 periods, 5 years, right? So you may want to get this value, but I'm going to go with this vector because this is easier for me. So in our appendix C, we are looking for 8%. You need to look at the page 611 and A given P over 5 years, which is 0.2505. This is 0.2505 times 5,000. Okay. So how much is that? This is going to be $1,252 even. Okay. Okay, next is about the example 4-4. An investor holds a time payment purchase contract on some machine tools. The investor will receive $140 at the end of each month for a 5-year period. The first payment is due in 1 month. He offers to sell you the contract for $6,800 cash today. If you otherwise can make 1% per month on your money, would you accept or reject the investor's offer. So we are working on example 4-4. So the problem is, should you spend $6,800 to buy a contract that pays $140 at the end of each month for 5 years if the desired return is 1% per month, right? So the given interest rate is 1% per month. So I is 1% per month, right? Not per year. And there are 60 months in 5 years, right? So the N becomes 60 months. And you remember both the interest rate and the number of interest periods must use the same period length, right? And the corresponding cash flow diagram would be like this. You want to know the present sum of P. And over the next 60 months, 1, 2, 3. Let's say here 58, 59, and 60. Uniform series of A equals $140, right? And the interest rate is 1%. So using the formula, P equals A times P given A, 1% over 60 period. So it's going to be 140 times P given A. What is this amount? So if you look at the appendix C, 1%. So you need to look at our text page 598, and P given A over 60 period is 44.955. This value is 44.955. And this value is $6,293.70. So what you need is compare this value with how much? With 6,800 that the contract will pay for you, right? So here, $6,800. So which amount is bigger? This one, right? This amount is a lot bigger than $6,293. So what is your conclusion? Because the contract only worth $6,293.70. So you need to reject the offer, right? The contract only worth $6,293.70. So definitely you need to reject the offer. Okay? Okay, then next, let's take another example. Example 4-5. If $6,800 is paid for the time purchase contract in example 4-4, what is the monthly rate of return? Okay, so here we are working on example 4-5. Now the situation is the present sum P is given as $6,800 and monthly payment for the next 5 years, which means for the next 60 months is $140. And we want to know the monthly interest rate, right? So again, the given information is present sum $6,800 and uniform series of $140 over 60 months, right? And in such case, we want to know the monthly interest rate. Okay. So cash flow diagram would be very similar to example 4-4, right? 0, 1, 2, 3, 40, no, sorry, 59 and 60. And the uniform series of 140. P is given as 6,800. Now we want to know the monthly interest rate here. So again, using the uniform series present worth formula, which is 6,800, P equals A, P given A, I percent over N periods. So 6,800 equals 140 times P given A and I over 60 period, right? So P given A, I percent over 60 periods is equal to 48.571. Okay? So if you divide $140, then the left-hand side becomes this value. So what you need is you need to find the desired interest rate, I, from the compound interest table. However, unfortunately, as you can see, the table in Appendix C do not include every possible interest rate or interest period. So just like in our case, there is no interest rate that provides uniform series present worst factor of 48.571. So for this value, the right factor can be found by using interpolation. So in order to use the interpolation, first, from the compound interest table, we obtain two interest rates, two closest interest rate, because we want to minimize the error. So first you need to find the two closest interest rate, which is 0.5% if I equals 0.5%, then this vector value P given A I over 60 periods equals 51.726. Okay, and another case, if I equals 0.75%, then this vector value becomes 48.174. Okay. So from the compound interest table, we obtained these two closest interest rate, having the values of 51.726, 48.174 respectively. Okay. And we want to find I value that provides this vector values equal to 48.571, right? So let's draw a simple diagram. So here the horizontal axis represents the interest rate, and the vertical axis represents this vector value P given A I% over 60 periods. Okay. If the monthly interest rate is 0.5%, then how much we have? It's going to be 51.726. So let's say 51.726 somewhere here. If interest rate is 0.75%, let's say somewhere here we have 0.75%, then the factor value becomes 48.174. So let's say 48.174. So we are right here. Okay. And if the monthly rate is I, somewhere between these two interest rate, then the corresponding factor value is 48.571. 48.571. So let's say before we do that, we need to connect these two lines to these 2 points. Okay. Now we're going to see that somewhere down here we have I% goes here. Okay. So our interpolation is rely on this diagram. And we have this small triangle. Let's say this small triangle is triangle A. And we can find the bigger triangle like this. Okay. So this bigger triangle is called triangle B, let's say. So our linear interpolation will be rely on these two triangles A and B. So the height of triangle A versus the base of triangle A is equal to the height of triangle B versus base of triangle B, right? That's what you're going to use for the linear interpolation. So let me write down here the height of triangle A versus base of triangle A equals the height of triangle B versus base of triangle B. Okay? So how do you get the height of triangle A? Height of triangle A is this amount, right? Which is 51.726 minus 48.571. So height of triangle A is 51.726 minus 48.571 versus how do you get base of A, which is this? That's going to be I% minus 0.5%, right? So I minus 0.5. Then how about height of triangle B? Height of triangle B is this amount, right? Which is 51.726 minus 48.174. So 51.726 minus 48.174 versus the base of triangle B. The same way, the base of triangle B can be obtained by 0.75 minus 0.5, right? 0.75 minus 0.5. So this value, the height of triangle A is 3.155 versus I minus 0.5, okay, equals, and the height of triangle B is 3.552 versus the base of triangle B is 0.25. So how do you solve this? There is the inner product equals the outer product, right? I minus 0.5 times 3.552 equals 3.155 times 0.25, okay? So I minus 0.5 equals 3.155 times 0.25 divided by 3.552. So I equals 3.155 times 0.25 divided by 3.552 plus 0.5, right? So what is the value of this? So from my previous calculation, it's going to be 0.22, okay? So 0.22 plus 0.5, which is 0.72. So it's going to be 72%, okay? So this is the monthly rate of return on our investment, okay? So from this example, we've learned how to use a linear interpolation in order to manually double check the accuracy of your interpolation. You need to keep in mind the following two basic rules, okay? So for double checking, the accuracy of your interpolation first, the interpolated value should lie between the tabulated values, right? So the interpolated value should lie between tabulated values. So in our example, the interpolated value of 0.72 lies between 0.5 and 0.75, right? Second, the interpolated value should be closer to one of the tabulated value, and only occasionally will be exactly in the middle. So the interpolated value should be closer to one of the tabulated values. And occasionally it will be exactly in the middle. Okay, so in our example, this value 48.571 is closer to 48.174 than to 51.726. So the interpolated value is closer to the tabulated value for 0.75 than to the one for 0.5 in this case, right? Okay, hold on a second, please. Okay, so next is example 4-6. So a student is borrowing $100 per year for 3 years. The loan will be repaid 2 years later at a 15% interest rate. Compute how much will be repaid. This is F in the following cash flow and diagram. For the 6, let me just double check. Okay. So we want to compute the future sum. That is the value of F, right? Here. However, the cash flow diagram here is not a standard form of the uniform series sinking fund vector diagram. So in this case, we have to think different way than you have learned earlier. So if the future sum F occurs 2 years earlier, which is right here, then we can use the uniform series sinking fund formula to compute F value. So suppose we have 0, 1, 2, 3, 4, and 5. And here we have 100 each. Example 4-6, right? And let's just suppose we have F3 right here. Okay? Then a uniform series A can be converted to an equivalent future value of F3 by using the uniform series compound amount formula. So here F3 can be obtained by 100 times F given A. And the given interest rate is 15% over the next 3 years, right? So what is this value? Factor value? Factor value is 3.472 times 100. So the F3 value is $347.20. Okay? And then what's next? This F3 value of $347.20 can be considered as a present sum P. So it can be converted to an equivalent future sum of F by using single payment compound amount formula, right? So what I'm going to do is 0, 1, 2, 3, 1, 2, 3, 4, and 5 here. And we can set F3 as a present sum P. Okay. Then the original future sum of F after the 5th year. Like this. So this F3 can be converted to an equivalent future value of F. Okay. So here F would be the present sum, which is F3. F3 times F given P, and 15% over next 2 periods, next 2 years, right? Here F3 is from previous calculation, which is $347.20, and this factor value is 1.322. Okay. So as a result, we're going to have $459.20. So these 2 steps can be combined into a single procedure like this. F equals F3. F3 is equal to this, right? So here F3 times F given P, 15% over period 2. F3 is equal to 100 times F given A, 15% over 3 periods. And then again multiply by this, right? F given P, 15% over 2 periods. Okay. And here's another way. You may think this given cash flow is a series of 3 single payments P. The single payments P1, P2, P3. And then compute the sum of future value F. That is, the given cash flow can be broken into the following three parts. So let's say here zero, 1 to 5. So we have here future sum F1, okay, and the first present sum of 100 at the end of first year, right, plus next future sum of money at the end of period 5 is F2, and 0, 1, 2, 3, 4. At the end of year 2, we have another P, 100, right, which is from here. And next cash flow diagram is at the end of year 3, we have P equals 100. And then at the end of year 5, we have future sum, let's say, which is F3. So this given cash flow diagram can be considered as a series of these three single payments P. Okay? So once you get those F values, three different F values, then you need to combine all three of them to obtain the targeted future value of F. Okay? So the original future value F is equal to F sub 1 plus F sub 2 plus F sub 3. Okay? So how would you get F1? That is going to be 100 times F given P, right? And then 15% over how many years? From 1 to 5 over next 4 years plus F2. F2 is again 100 times F given P, 15% over how many years? 3 years, from 2 to 5, right? Plus 100 times F given P, 15% over next 2 years, from 3 to 5. Okay? And these factor values can be obtained from the compound interest table, Appendix C. They are 1.749 plus 100 times 1.521 plus 100 times 1.322. And as a result, you will get $559.20. And this result should be the same as the one from the previous method, right? Here. So we have two same values. So obviously, there are a couple of different ways to get the solution. And you need to choose the better methodology to save your time and all the computations. Okay. Okay, I'm going to stop here for today. And next time, I will continue to talk about chapter 4. And then, if time allows, and then we're going to solve the end of chapter 4 problems next time. Okay, thank you. Bye-bye.